Hello, everybody. So this assignment is exclusively curated regarding the questions of approximations that are used in determining the rate of the reaction. Okay, so we have 10 questions. Let's start. First question is, hydrogen plus Br2 react to give HBr by the following steps. So they have given 3 steps, and in all the 3 steps, they have mentioned which steps are fast, which of them is slow, and they have also written that the equilibrium constant is equal to K1 by K inverse. You have to write the probable rate law for the above sequence. Okay, so the first thing that we should know is the rate determining step is always the slowest step. The rate determining step is always the slowest step. So rate is equal to the slowest step over here is second step, where the rate constant is K2. Concentration of the reactants would be Br and H2. Okay, so K2 Br into concentration of H2. So out of which in the question they have said that in the reactants, they have used only H2 and Br2 as the reactants, correct? So we have the inclusion of Br in this statement and we need to remove that, correct? So how can we remove that? Already it is given that the equilibrium constant is given. These steps are fast. That is also given. So let's try equilibrium method to eliminate Br from the system. Okay. So from the first step, I'll copy it down. So from the first step, capital K is K1 by K inverse, and that is going to be equal to, on the product hand side, you have Br to the power 2 into M, this is equal to, divided by Br2 M. Okay, M and M gets cancelled. And what you have over here is equilibrium constant is equal to Br2 divided by Br2. This is what you get. Right, now you need to replace this Br over here. So equilibrium constant, concentration of Br2 is equal to Br squared. And if I have to take the concentration of Br only, we'll take the root. Right. This is equal to Br. So we'll put this expression of Br over here and let's see what we get. So what we get over here, so let's say if this is 1 and if this is 2, and if I put 2 in 1, I get rate is equal to K2, concentration of H2 into capital K to the power 1 by 2, Br2 to the power 1 by 2. So let's see if we have an option of that sort. K2, K to the power 1 by 2, H2, Br2 to the power 1 by 2. The correct option is option C. Removed by equilibrium method. Okay. Next question. A following reaction which occurs in 3 steps. It is given. So 2NO plus O2 gives 2NO2. You have to write the rate of this reaction. Rate of this reaction is equal to. So as in the question, they have not mentioned which is the slowest step. If that is not mentioned, the step where the product is being formed will be taken as the rate determining step. Okay, so over here, this will be taken as a rate determining step. Now, if that is taken as the rate determining step, what we'll have is rate is equal to Kb, concentration of N2O2 into concentration of O2 is what you have. Now let's look at the reaction. We have NO and O2 as the reactants, but then now what you have over here is N2O2, which will act as the intermediate, and you need to remove the intermediate. Now, in order to remove the intermediate, we have two ways. One is the equilibrium method and the other one is the steady state approximation. Over here, you cannot adopt the equilibrium method because no equilibrium processes are there. So we have to proceed with the SSA, steady state approximation. And you need to put the steady state approximation on the intermediate. The intermediate that we have is N2O2. So according to which the steady state approximation is the changes in the concentration of the intermediate with respect to the time will be taken as 0. Correct, will be taken as 0. Now, if you see in the first step, N2O2 is being formed. So if I have to write the individual steps, for example, over here, N2O2 is being formed, and that is going to be equal to Ka, concentration of NO to the power 2. Over here, N2O2 is disappearing, and I can write it as Ka prime into concentration of N2O2. And the last step as well, N2O2 is disappearing. And I can write it as Kb into N2O2 into concentration of O2 is what I have. Correct. Now what I need is positive dN2O2 by dt. And here there is minus, I can take it to the right, so this becomes plus. I'll take this negative to the right, so this becomes plus over here. Correct? Now, cumulatively, dN2O2 by dt is the summation of all of these. Correct. So, what are those? That is equal to dN2O2 is equal to Ka NO square minus Ka prime N2O2 minus Kb N2O2 into O2. Correct. And this is going to be equal to 0. Now we need the expression for N2O2. Let's rearrange. So what we have is Ka NO to the power 2 is equal to Ka prime plus Kb into O2 and N2O2 taken out. So if I rearrange this, concentration of N2O2 can be written as Ka concentration of NO to the power 2 divided by Ka prime plus Kb into concentration of O2. Now, if this is 1 and if this is 2, I'll put 2 in 1. So what do I get? I get R is equal to Kb, concentration of O2, into Ka, concentration of NO to the power 2, divided by Ka prime plus Kb O2 is what I'm getting. Now let's check the options. So if you look at the options, what you can see is Ka, Kb, O2, NO2 square divided by Ka prime plus Kb into concentration of O2 is already there. But a 2 is missing. A 2 is missing. Now, actually, if the rate of the reaction is the question, this was supposed to be the answer. But what they have done over here is, please look at the reaction. Please look at the reaction. So if you look at the reaction, what you can see is rate of the reaction in terms of the productive written. Rate of the reactions in terms of the productive written, it is written as rate is equal to, in terms of the product, 1 by 2 dNO2 by dt. Correct? So this rate is equal to 1 by 2 dNO2 by dt. Or if I ask you to write the rate of the product formation, only 2 will go to this side and it will become 2 Ka, Kb, concentration of O2 into concentration of NO to the power 2 divided by Ka prime plus KbO2. So they actually had put the question in terms of the rate of the reaction, which is this expression what you see. But as it is not there in the question, we have arranged it into the formation of the product. We have arranged the expression into the form of the formation of the product, wherein we have got this 2 included, and hence the correct answer to this question is option B. Option B. Okay. Next question. The decomposition of O3 to O2 occurs by these mechanisms. For each of these mechanisms, they have given the rate constant. Now, if M is the catalyst under steady state approximation, you have to find the rate of decomposition of O3. Okay, you have to find the rate of decomposition of O3. Now, so what is rate of decomposition of O3? It will be minus dO3 by dt is what you have to find, the expression. Now, there are 3 steps given. Again, they have not mentioned which is the slowest step. So if that is not mentioned, the last step where the product is being formed will be taken as the rate determining step. Correct. So let's start. What you have over here is rate is equal to K3 concentration of O3 into concentration of O. This is what you have. Correct. Now we have a process where ozone is decomposing to oxygen. So ozone is our reactant and oxygen is our product. What we have in our expression is O, and this O is going to be an intermediate. We have to remove it. How are we going to remove it? We are going to remove it using SSA. Correct? So I'll copy paste. This over here, so that I can write the expression. Okay. Now we need to write the expression for the steady state approximation when applied on the intermediate O such that dO by dt is equal to 0. Correct? So we need to write it for dO by dt. Now if you can see, O is being formed in the first step, disappearing in the second step, and again disappearing in the third step as well. So what will be the form? It will be dO by dt is equal to, it is being formed in the first step, right? So it will be K1 into concentration of M into concentration of O3. In the next step, it is disappearing. So minus K2 into concentration of O2 into concentration of O into concentration of M. And in the final step, again, it is disappearing. So that is going to be equal to K3 into concentration of O into concentration of O3. This is what you have. All right. And you know that this is going to be equal to 0 because it is steady state approximation. Now, under steady state approximation, if you rearrange and find the expression of O, let's do that. K1 concentration of M into concentration of O3 is equal to K2 concentration of O2 into concentration of M plus K3 into concentration of O3, and I take O out, common. So if I write the expression of O, that is going to be equal to K1 concentration of M into concentration of O3 divided by K2 concentration of O2 concentration of M plus K3 into concentration of O3. Right. This is what I have. Now I have got the expression for O. I have got the expression for O. Now see in the question, they have not asked us to find the rate of the reaction. They have asked us to write the expression for the decomposition of ozone. They have asked us to write the rate corresponding to the decomposition. So now let's write the expression for the decomposition of ozone. You can see that in the first step, ozone is disappearing. In the second step, nothing is happening. No, in the second step, ozone is being formed, and in the third step, it is disappearing. Correct? So you need to write the expression. Now let's number this. Let's say that this is 1. We have got the expression for O, which is the intermediate, and I have numbered it as 1. All right. Now we have to write the expression for dO3 by dt. So in the first, this is disappearance, okay? This is disappearance. So in the first step, it is disappearing, correct? So this will be K1 concentration of O3 into M. In the next step, it is being formed, but what you need is disappearance. So you will put a minus, correct? And that is going to be equal to K2 concentration of O2 into concentration of O into concentration of M. The last step also, it is disappearing. So you will get the expression for minus dO3 by dt, and that is going to be equal to plus K3 concentration of O into concentration of O3. This is the expression. Okay. Now, wherever you have O, you can see that you have O over here, you have O over here, you have to put it. Let's say this is equation number 2. You have to put the expression of O in 2. And let's see what we get. Okay. So what we get is minus dO3 by dt is equal to, in the first term, it's not there, K1 O3 M. In the next term, you have M and O3 on the numerator of the expression corresponding to the oxygen. And here there is also M. Okay, so I'm writing it together. Please be careful when you plug in the values. It's going to be minus K1, K2, O2, O3 M squared divided by K2 O2 M plus K3 O3. Okay. Now in the final term also you have to plug in the value. So this will be K1 K3 M O3 to the power 2 divided by K2 O2 M plus K3 O3. Okay, now you have to take the LCM. In the second and third term, the denominator is the same. You have to make the same denominator appear over here as well. So we'll cross multiply. Minus dO3 by dt is equal to. So when you cross multiply, K1 into K2 O2 O3 M squared, okay, plus K1 K3 O3 squared M, okay, that's it, minus this term, K1 K2 O2 O3 M squared plus K1 K3 M O3 squared. The whole divided by, now you have a common denominator, which is K2 O2 M plus K3 O3. Now if you check the terms, the first and the third terms are the positive and negative of the same value. The second and the fourth term are the same. So when you add them, you get minus dO3 by dt is equal to 2 times K1 K3 O3 squared into M divided by K2 O2 M plus K3 O3 is what I have got as my final expression. Let's check the answer. 2 K1 K3 O3 square M divided by K2 O2 M plus K3 O3. Okay, this one. Correct answer is option A. Correct answer is option A. This was a beautiful question asked in 2011. And mark this question as important. Okay. A bit lengthy, but then easy. Okay. Next. A very easy question. I think this question was repeated in NET as well. For a reaction involving two steps which are given below, G giving 2H and G plus H giving P. Assume that the first step attains equilibrium rapidly, means this is fast. The rate of the formation of P is proportional to. Okay, so the rate of the product formation is equal to whatever, now let's say that here it is K1, it is K inverse, and it is K2. It's not given, but let's assume. So rate is equal to K2 into concentration of G into concentration of H is what you have. Out of which H is the intermediate. You can see that H is the intermediate and you have to remove the intermediate. For that, you can use the equilibrium method because the equilibrium expression is given. Correct. So equilibrium constant is going to be equal to H to the power 2 divided by G. Now, if I have to rearrange, concentration of H is equal to K equilibrium into G, the whole raised to 1 by 2 is what I have. Now I'll put this value of H over here. Correct. If I put this value of H over here, what we get is rate is equal to K2 into concentration of G into K equilibrium to the power 1 by 2, G to the power 1 by 2. As a totality, you can write it as R is equal to K2, K equilibrium to the power 1 by 2. This is G to the power 1. This is G to the power 1 by 2. In combination, you will get it as G to the power 3 by 2. The correct answer is the rate of the formation of the product P is directly proportional to G to the power 3 by 2, option B. Option B. Yeah. Okay. Question number 5 is very easy. For the first order consecutive reaction P giving Q giving R, under steady state approximation to Q, the variation of P, Q, and R with time are best represented by. So we know that in a steady state approximation, whatever the intermediate is, over here it is Q, the changes in the concentration of the Q, that is dQ by dt, will be nearly equal to 0. That means it will be attaining stability. Correct. So in that sense, you know what the answer is, this one, option C. We have already written the notes in the class. We have already discussed it. So the correct one is option C. Very good. Okay. This question is a bit lengthy, but then very easy. It's a statement type question. Let's read the question. The formation of Z from X is theoretically expected to obey the following kinetic scheme. So there is a scheme which is given where X forms Y and then Y forms again Z in a reversible manner. An experimentalist wants to verify the above scheme but can observe and measure the concentration of X and Z only. Okay, so whoever is measuring the reaction, whatever parameters of the reaction, is capable of measuring the concentrations of X and Z only. Is it possible that under certain conditions, the measurements of the concentration of X and Z as a function of time would lead to an experiment to conclude that the kinetic scheme is as given below? That is, X is reversibly becoming Z, Y species is absent. It's like Y species is not even there. Okay, so that happens because the changes in the concentrations of the Y is negligible to 0. And when does this happen? The options are all given over here. The correct option is option D. It's because D has attained steady state approximation in such a way that the small concentration changes of Y, because the moment Y is formed, it disappears into Z. Okay, that is a criteria of SSA. So it's a statement type question which was asked in TIFR. It looks lengthy, but then it's very easy. Okay. Easy question, numerical 1. For A plus B reversibly forming I, which again forms P, if SSA is applied on I, the observed rate constant of the product formation in this particular unit is. Okay, it's very easy. So let's start. The rate formation is going to be the step where the product is being formed, which is K2 into concentration of I. Okay. Now, if I have to put the steady state approximation on I, so I'll label this as 1. Now, steady state approximation on I will give me changes in the concentration of the intermediate as equal to, in the first step, I is being formed. So it's going to be K1 into concentration of A into concentration of B. In the reversible step, I is disappearing, so minus will come, and that's going to be equal to K inverse concentration of I. In the final step also, I is disappearing, and it will become minus K2 concentration of I. This is going to be equal to 0. Correct. Now, if I rearrange this, K1 concentration of A into B is equal to K inverse plus K2 into concentration of I. And the expression for the concentration of I is equal to K1 A into B divided by K inverse plus K2. Now, if I put this equation as 2, I'll plug in 2 in 1, and the rate expression that I'm getting is rate is equal to K1, K2, concentration of A into concentration of B divided by K inverse plus K2. Correct? So from this expression, I have got the value of effective rate constant, which is K1, K2 divided by K inverse plus K2. Now I need to plug in the values, that's all. What is the value of K1? 10 to the power 5. You please put in the values as well, units as well. 10 to the power 5 liter per mole per second into K2. Correct. What is the value of K2? Value of K2 is 10 per second and divided by 10 to the power 4 per second plus 10 per second. Okay, so 10 to the power, okay, now if I solve this over here, what I get is 10 to the power 5 into 10 is 10 to the power 6 liter per mole per second squared divided by 10 is common over here. I take that out. So I get 1000 plus 1, 1001 per second. Okay, so per second gets cancelled. So what I have over here is 110 and 110 over here also get cancelled. So what I have over here is 10 to the power 5 divided by 1001. Liter per mole per second. You need to numerically solve this. That's all. You have got the approach. So by solving this, what I'm getting is 99.90. You have to round it to 2 decimal places with this particular unit. So we have got the unit and you need to round it off. The answer key had given 99.85 to 100. This range, any value that you put with 2 decimal places would be valid. Okay. Next question. The elementary steps of a reaction are as follows. Now be careful whenever you have coefficients. Be careful. If SSA is applied to C, the rate of product formation in the reaction is very easy. Rate of the product formation is dD by dt. Correct? And that is going to be equal to K2 into concentration of C to the power 2. Correct. Because that is the step where the product is being formed. Very easy. Now, as you can see, C is an intermediate. So it is formed in the first step, it is disappearing in the next step. So this is the intermediate which you have to eliminate. So if you have to eliminate that, you need to apply SSA as said in the question. So let me write it step by step so that you don't get confused. So in the first step, why isn't it changing? In the first step, A plus B with a rate constant of K1 forms 2C. Okay. So from this, the rate of the reaction is 1 by 2 dC by dt is equal to K1 into concentration of A into concentration of B. All that we need is dC by dt, and that is going to be equal to 2 times K1 A into B. Remember, 2 times K1 A into B, that is there. Okay. So in the reversible step, what is happening? 2C is becoming A plus B with a rate constant of K inverse. So here, disappearance of C is what is happening, correct? So if I have to write the rate of the reaction, let's say, minus 1 by 2 dC by dt is equal to K2 into concentration of C to the power 2. But what I want is dC by dt. So I'll take this 2 to the other side, minus to the other side. So what I have is minus 2K2 C squared. What I have. Oh. In the last step, 2C is becoming D with the rate constant K2. Here also disappearance is happening. So if I have to write the rate of the reaction, this is going to be minus 1 by 2 dC by dt. That is equal to K2, concentration of C to the power 2. Okay, I'm sorry. Here it is K inverse. Okay. And if I have to rearrange for dC by dt, that is equal to minus 2K2C squared. Correct. Now I can combine all these and get the cumulative effect of dC by dt, that is equal to 2K1 A into B minus 2K inverse C squared minus 2K2 C squared is equal to 0. So if I rearrange 2K1A into B is going to be equal to 2K inverse plus 2K2 into concentration of C squared. Okay, now we'll rearrange in terms of C squared. That is going to be equal to 2's are common. I cancel out 2's. K1 concentration of A into concentration of B divided by K inverse plus K2. Right. So we had to eliminate C squared. We have got the expression for C squared. So the rate of product formation is equal to, expression is K1, K2, concentration of A into concentration of B divided by K inverse plus K2. This is the expression. What is the question? They have asked the relation. The rate of product formation is proportional to A and B. Proportional to A and B. Correct answer is option A. Option A. Easy. Very easy. Okay. Next question. You have to be careful with the coefficients. That's all. That's why I did this in detail. Okay. Next question. So the decomposition mechanism of ozone is shown over here. And they have said that if K inverse O2 is very much less than K2O3, then the order of the reaction with respect to ozone is. So you have to read the question very, very carefully. They have asked the order of the reaction for which you need the rate of the reaction, of course. Correct? So rate of the reaction is going to be equal to, they have not mentioned the slowest step. So we need to take the final step as a rate determining step, that is equal to K2, concentration of O3 into concentration of O. Correct. Now this is the decomposition mechanism for ozone. So ozone is the reactant and O is the intermediate which we have to remove. We have to remove. How will we remove? We'll have to apply the SSA. So let's say this is equation number 1. Let's apply SSA. dO by dt. In the first step, it is being formed. So that is K1 into O3. In the reversible step, it is disappearing. So you have to put minus K inverse O2 into O. In the final step also, it is disappearing. So minus K2 into O3 into O. This is going to be equal to 0 according to SSA. Now rearrange and find the expression for O. So what I get is I'm directly writing the expression. K1O3 divided by K inverse O2 plus K2O3 is going to be equal to your concentration of O. This is equation number 2. You will plug in this value of O in your rate expression. So your rate is going to be equal to K1, K2, concentration of O3 to the power 2 divided by K inverse O2 plus K2O3. This is your actual expression. But see what is given in the question? They have said that your K2O3 value is very, very, very high than K inverse O2. Okay, what they're saying is this value is very, very, very high than K inverse O2. So you will neglect K inverse O2. Correct? K inverse O2 is very much less than K2O3. So your rate expression now is K1, K2, O3 to the power 2 divided by K2 into O3. K2, K2 gets cancelled. 1, O3 gets cancelled. So your rate is just K1 into O3. What is the question? What is the order with respect to O3? 1. Order is 1, option B. Option B. Oh, last question from the set. The oxidation of NO to NO2 occurs via the following mechanism. Mechanism is given to you. So the question is dNO2 by dt, which is the product formation. dNO2 by dt is the product formation. In the presence of large excess of O2, large excess of O2 can be written as. Okay, so let's start. We have to get the rate of product formation. So rate of product formation is dNO2 by dt. And that is equal to, from the last step, it is K2 into N2O2 into O2. In the question, they have given that NO is being converted to O2. And from the mechanism, you can understand that N2O2 is the intermediate. So you need to eliminate that. How do you eliminate? Again, through SSA. So let's apply SSA on dN2O2 by dt. That will be equal to 0. In the first step, that is being formed. Correct. So K1, concentration of NO to the power 2. In the reversible step, it is disappearing. So K inverse N2O2. In the last step also it is disappearing. So minus K2 into N2O2 into O2. I have made a mistake over here. Over here. So the rate of the reaction is 1 by 2 dNO2 by dt. And that is equal to K2 into N2O2 into O2. So please be careful. The rate of the reaction is 1 by 2 times NO2 by dt according to whatever equation there. Okay. All right. So from here, we'll rearrange and find the expression for NO2. This is going to be equal to 0, correct? Because it is SSA. This is going to be equal to 0. So that is K1 NO square divided by K inverse plus K2 into O2 is the expression for N2O2. We will use this N2O2 over here. So let's see what happens. What we get is rate, which is 1 by 2 times dNO2 by dt is equal to K1 K2 NO square into O2 divided by K inverse plus K2 O2. Now, if you need just dNO2 by dt, you will take 2 to the side. And this is going to be your equation. Correct. Now, what is the question? In the question, they have said that you have a large excess of O2. So if you have a very large excess of O2, you will look into the denominator where the amount of oxygen present is so high that you neglect this. You neglect the other term because oxygen, the level of oxygen in the system is very high. So if that is the case, dNO2 by dt becomes 2K1 K2 NO square into O2 divided by K2 O2. Now O2 is there in the numerator, O2 is there in the denominator, K2 is there in the denominator, K2 is there in the numerator. So overall, what we are getting is 2K1 NO squared is what we are getting. Let's see if we have an option. 2K1 NO squared, option A. 10A, correct. Okay. Okay. So yeah, this is how we approach questions from approximations. This is a very beautiful set, and this is my personal favorite. As you can see, you get a lot of questions from this area. And if you practice well, you can easily score marks. Okay? All right. So practice well. See you in the next session. Bye-bye.